Welcome back, Quadrature fans. My name is Mary and Elena, and today we'll tackle the subject called Geometry for Quadrature, a very needful subject. And essentially, it's the geometry that's kind of necessary to help understand, well, Cavalieri's principle, Cavalieri's principle is basically, you've seen a deck of cards, and it has area. It has volume, but we'll focus only on the area. And the area is invariant. No matter what you do to this thing, you can shift it nice, linear, like this. See, everything is nice, parallel. The area is the same. You agree, right? I haven't changed the area because the number of cards, that's the same. They each have a certain thickness. So, well, let's look at this. Here's a curve y equals x squared. And you've seen this. And typically we plot it, and these are perpendicular at right angles. We normally plot it this way. Is this the Cartesian system, René Descartes? Is this Euclidean? I don't know. In either case, we typically plot it like this. And that would be the curve y equals x squared. But the algebra doesn't dictate that you plot it this way. There's nothing that says you have to plot it that way. As a matter of fact, you can plot it some other way. You can shift things around. Here we plotted it a little bit different way. Notice we're maintaining parallelism this way, but we're shifting things. Kind of like Cavalieri's principle, right? And I've taken this thing here, this top, and I've just tweaked it, and so this would be an example of affine geometry. This one, what did we call this one? Cartesian. Now there's a Euclid. That's this one. This one is affine. And you can see that that's essentially the geometry of Cavalieri shift. We are maintaining nice parallels right here. These are completely parallel, right? And so we can plot it this way, y equals x squared. And the algebra doesn't care, right? That's fine. Well, let's go further. Here's an example of kind of an affine system, but it's curved. That'll be kind of closer to this, Let's just say it's like this, right? It's curved. Again, the area is unchanged. We're maintaining parallelism this way. See all these lines that are parallel. But here, clearly they're curved. And here's a notion of affine parallelism, but the parallels are only here. These are parallel. See how they're parallel? It's curved parallelism. That's how I call it. There may be a better term for it, but I don't know. What would I call this? Does this thing have a name? What name shall we call this? Kind of Cavalieri, right? Cavalieri. Cavalieri. Did I spell it right? I don't know. But anyway, so that's Cavalieri right there. And we are maintaining strict parallelism this way, but over here we are allowing to be curved, and these are always parallel. See, everywhere you go here, that's parallel. See these parallels? They are there. There's parallelism. And of course, under all these shifts, we notice that the area is definitely invariant. The area did not change, even though we changed things around. We shifted things. Well, let's go even more wild. Check this out. Ooh. Here is kind of the notion of curved parallelism, but just like this one, see this curvature here? So there's parallelism this way, but there's also parallelism this way. You see it? In other words, we can take this shape over here, see this shape? And imagine I draw this shape right here, and then I do a kind of a curve on it, right? I do an S-curve. I can do that on this shape. Have I changed the area of any of these? No, it's invariant. You see it? Now, we got to give a name to this one. And the name that I give it is the Salvador Dali. That's the name of this one, right? That's, where's our Salvador Dali? See this? Check this out. There's this picture, right? That's Salvador Dali. He's a painter of weird geometry. That's pretty neat, huh? You got that? Alright, so that's Salvador Dali. Now, it turns out that in Quadrature, we don't need Salvador Dali, so let's forget about him. But I just want to point out that the algebra doesn't really care. He's just as happy over here as he is here, as he's here, as he's here. It doesn't matter. So Salvador Dali's okay for the math. But we're not going to use that. That's a little bit too wild. But this, the notion of curved parallelism, or affine, but affine is strictly parallel here, parallel here. That's nice, and nice feature about this affine geometry, as well as this one. You can shift this. See how I shifted it? You can shift this thing a distance of 1,000 kilometers if you wanted to, and it would still be the same area. It would just be very thin, but there's no restriction on how far you can go with this shift. You can go to the moon. It doesn't care. The area is still the same. And the weird thing in affine geometry doesn't kind of know. It doesn't have a concept of perpendicular. It doesn't, and it can't tell. You're affine this way. What if you switched it around? What if you went this way? It couldn't tell. To affine geometry, this is the same as this. It's all the same thing. As far as the area is concerned. And with Cavalieri type geometry, which is affine but it's curved, so it's a curved affine, think of it that way. Again, you can't distinguish between this and whatever weird shape you want. I mean, they're all curved, but the area is always the same. Now, the question that I had was, well, what about the slope? Particularly this diagonal slope. You see this? In our little world, our Cartesian world or Euclidean world, whatever, this is the kind of world that we're comfortable with, right? Everything's at right angles. We can tell that it's right angles. We look at this diagonal and we say that's as straight as an arrow, right? And well, we look at this one over here in affine geometry. The diagonal lines are preserved, but it's a different, to us at least, it's more steep. You see, this is steeper, right? In the way I pictured it. Looking at it from our Cartesian viewpoint, our Euclidean viewpoint, we look at affine and we say, okay, yeah, it's constant, but it's steeper. It's not the same. It's not unchanged. You would think that slope has definitely changed there. That's kind of a reasonable conclusion from a Cartesian perspective. However, if, let's say that you're an amoeba that lives inside of this box, and you don't have this big picture view. All you know is you have this nice kind of a grid over here, and you have some rise over run, and so you're an amoeba and you're going along, and for every so much run you get so much rise, and it's constant, and so you conclude, and the constant is, well, in this case it's 4a squared over 2a. Well, that's the same, 4a squared over 2a. That you conclude as an amoeba that the slope of this diagonal is 4a squared over 2a. But you conclude the same thing over here, 4a squared over 2a. It's kind of an interesting discrepancy. Think of it this way. We live on a planet, right, which is a sphere. But at least to me, I look out and I see everything flat. So, as an amoeba, you're looking at the world and you say, well, the world is flat. And that's a reasonable conclusion because it looks that way. I can't tell. And maybe I have a map. And then I go, rise over run, and it's all the same, as an amoeba, you can't tell that this thing's different. All you can do is you conclude that the slope is 4a squared over 2a. And the same thing over here in this curved scenario, just like our flat Earth, or is it spherical Earth? I don't know. To me it looks flat, but I don't know. So, okay. So here, definitely this, to us it looks curved, but to the amoeba, it's as straight as an arrow because it's 4a squared over 2a. That's its, 4a squared 2a. So, slope is also invariant within this system of geometry, this affine or this affine Cavalieri style system. And Well, we're going to employ this. So let's continue our discussion of geometry for quadrature. I had an opportunity to draw some more stuff on my whiteboard. And so basically we have our y equals x squared, and we're going to do translation at x equals a plus t. 0a. You've seen that before. So you plug in y equals a plus t squared, and lo and behold, you get this nice equation, which of course you remember that is related to our Pascal's triangle. These coefficients, they're all related. And so, yeah, you have a constant term, which is this thing. It's a rectangle. A linear term, which looks like a triangle, right? It has a steady, constant slope. And then a quadratic term, which looks like this, right? So, you know, that's what it looks like, at least in a Cartesian type system. So let's look at the slope at point P. That would be the tangent slope right here, right? That's what we're after. This tangent slope at point P. Well, from the x perspective, that's the point where x equals 2a, right? That's the d, which stands for tangent slope. That's our box operator. You've seen that before. Of x squared, evaluated at x equals 2a. And that equals the tangent slope of basically all of these little functions of t, evaluated at t equals a. Remember, t here is a, here t is 0 here, here x is 0 here. That's the translation, a. That's our translation. And so, from the x perspective, we're looking at this, and the slope we're looking at, and that's slope d at x squared, of x squared at x equals 2a. Well, that equals the d of a squared plus 2at plus t squared evaluated at t equals a. Well, what is that? That's our simple box operators that you've seen before. C2, so we have squared, times the diagonal, this diagonal. C2 is this constant, invariant, that multiplies our diagonal, and that gives us the slope at x equals 2a. And so what is the slope here on the t functions, these little functions? See these three functions? They look like this: constant, linear, quadratic. Okay. So we know that C0 is 0. That flies out of there. C1, that's our linear. Well, that's always a 1. And basically it's 2a, you plug in t equals a, and you get 2a squared over a, which we could see the slope is 2a right away. And then for the quadratic, c2 is our unknown, and again the rise is a squared, the run is always a. And so there's our basic setup. And for slope, and you can see that the a squared over a will fall out of there, so that's gone. So let's reconfigure it here. So that's C2 times 2 equals 2 plus C2. Well, throw that C2 over here, solve, and you get C2 is equal to 2 right away. Pretty simple, huh? Okay, well, let's actually look at this thing a little bit more geometrically, okay? We're saying, particularly here on these little guys, the slope of our rectangle, that's always 0. See? These little slopes, the slope here plus the slope here plus the slope here, adds up to the slope over here from the x perspective. So, okay. Kind of let's look at this in an affine perspective. So, let's see. So I have my rectangle here, and then I add my triangle here, and then this is a squared, 2a squared, 0 to a, and then we said over here, that's our quadratic, a squared. And remember, this is on a, let's get another color here. The box that we're starting out with is like this. And essentially we're going to use Cavalieri's principle and shift it down, and it's going to look like this right there, right? And so when we do that under a Cavalieri operation, and so let's downshift it. So the box, same height. Oh, this thing doesn't work. I'm going to use my black pen. Okay. It's going to look like this. And then, see this? When we downshift it, see this? What have I done? I've basically, imagine that I draw a picture of my quadratic here, and now I downshift it. Okay? That's going to look like this. See this picture here? And this diagonal is going to look like this. Now, oh, it's beginning to look messy. But you can see what we did was essentially we went from here to here, and it's the same thing. In essence, in our Cavalieri geometry, we cannot even distinguish between this area here and this area here. They're equivalent or equal. Because in Cavalieri style geometry, well, you can do anything you want with this thing. It's the same. Well, it's the same for area, but it turns out that the slope, this is a tough one to understand. I'm trying to understand it myself. You know, to us it looks like the slope is definitely changing, but if you're within this system, this affine type system, you can't even tell that your slope is changing. To you, it's all invariant. And so it all adds. So these these two areas are totally equivalent. You know, and that's, you can see that going from 0 to A on the x-axis is the same as going from 0 to A on the t-axis right here. But, you know, you just shifted it. But the relative slopes, they're the same. They can add. And that's kind of an interesting finding that you get with this affine and curved affine geometry. The algebra really doesn't care that, which way. What about the order? Could you swap the order around? T squared plus 2at plus a squared? You certainly can. And it would look different over here. You probably have t squared, and then you have a squared 2a squared, something like this. Okay, and it's the same thing. Areas are the same. You do a Cavalieri shift on all of these, you end up with this wedge over here. And that's pretty cool. So, yeah. And the area, that's our S of x squared evaluated at x equals 2a equals this little guy, the signed area of x squared, still from the x perspective, but it's evaluated at x equals a, because we want this little guy. And then these three areas plus the signed area of a squared plus 2at plus t squared, right? So, what's going on here? Okay, evaluated at t equals a. We're using our notation for sine area and tangent slope. D is our tangent slope, S is our sine area. Okay, so this will look like a K2 times the box evaluated at x equals 2a equals, well, this is K2 times the box of this thing evaluated at x equals a plus, well, this one is K0 times his box, right, that's the rectangle, plus K1 times, that's the triangle, the linear, plus K2 times his box. All of these evaluated at t equals a. Okay? So let's crank that. That's going to be K2 times, well, guess what? It's the rise, 4a squared, times 2a, times the run. That's it. Equals K2 times a squared times a. Because here's a squared, here's a, that's this box. Plus, now we got to pick up these three areas, and that's K0, it's 1 times, that's a squared times a, right? Times a plus the triangle, that's 1/2, right? 1/2 of 2a squared, 2a squared times a, yeah. Yeah. Height times base, and then plus K2 times the third one, which is, I'm getting confused. Yeah, that's, the rise is a squared, the run is a, so a squared times a. Notice that this is the same as this. And this is the key. And this is why you need that geometry for quadrature, is that it's indistinguishable. The algebra is telling us that the area is indistinguishable. It's K2 times a squared over a. That's for this guy. That is identical to this one here. You see that funny looking thing? It's indistinguishable from an algebraic perspective. It's K2 times a squared over a. These are one and the same. And that's this affine Cavalieri geometry, which is not evident in our Euclidean, René Descartes, whatever that we're used to me. You look at this and you say, this looks totally different from this. But under a Cavalieri shift, it's not different. It is one and the same. It's the same thing, and you can't even distinguish within the system. You cannot distinguish this from this from this. They're all the same. It's the same within this system, this curved system. It's the same for area, and strangely, I may misunderstand this, but it's even the same for slope. Within that system, if you're an amoeba that lives inside here and you've got this nice grid, you can't tell that you're curved or crooked. There's no way you can tell. You're going by rise over run or rise times run. That's all you know. That's the algebraic perspective. And so we're trying to get, marry the algebra to the geometry, or, which, trying to understand essentially this Cavalieri principle, this shift, what's happening behind the scenes. So anyways, let's continue with this. The a squared times a squared times a, that cancels out, that just falls out, so we're left with K2 times a equals K2 plus 1 plus 1 plus K2. So you got solve one equation, one unknown, 6K2 equals 2, K2 equals 1/3, right? K2 equals 1/3, which we already knew, but that's how it's, it just simply falls out. But the key point that I want to drive home is, from an algebraic perspective, this thing here, the sine area of x squared evaluated at x equals a is the same as the sine area of t squared evaluated at t equals a. It's indistinguishable. And within this Cavalieri style system, you cannot distinguish this area from this area. You can't distinguish it from the area perspective. You cannot distinguish it even from the slope perspective. That's what I'm saying. I may be wrong, but I welcome your feedback. But that's kind of the thing that hit me with this affine type Cavalieri geometry, is that the slope itself is invariant within this system. It's kind of a weird geometry, but we're used to this. And here things are, I see a line. Here's a crooked line, you say, but within the system, you can't tell that he's crooked. Because he's a curved affine, and he's got, there is parallelism, just like this one is purely parallel. You got straight parallelism this way, and then you got parallelism this way. You can see that. Here it's curved parallelism, and that's the kind that I think that we need for geometry for quadrature. This kind of a curved version of the affine geometry. So, welcome your comments. Okay, so as Professor Taylor-Amos Antiquitus would say, before there was calculus, there was all this stuff.
There was quadrature.
Yay! You got it.